Today's lesson is VSEPR theory. VSEPR, valence shell electron pair repulsion. Valence shell electron pair repulsion is the today lesson. Right, what is meant by VSEP? VSEPR means valence shell electron pair repulsion. When you take any atom, for example, as a sodium, it has 11 electrons. 11 electrons. So first energy level has 2 electrons. Second energy level has 8 electrons. And third energy level has 1 electron. So valence shell is the outermost energy level. Valence shell is outermost energy level. When we take an atom, it has only electrons, means single electrons, and paired electrons with the other atom. But when you take molecule like ammonia, ammonia is a simple molecule. Bonds form in between nitrogen and hydrogen atoms. So when you draw the structure of ammonia, this is the Lewis structure of ammonia. You can see around the nitrogen atom, it has 3 NH bonds and 1 pair of electrons we call lone pairs. So this one we call lone pair. This one we call bond pair. Always bonds formed by electrons in valence shell. Valence shell is outermost energy level. Valence shell is outermost energy level. Innermost energy levels we call core shells. Core shells. Core shells have completely filled with electrons. The number of electrons that occupy in the first energy level, maximally 2. The second energy level, 8. So they have completely filled with electrons. But valence shell has less number of electrons, means less number of electrons than 8. Therefore, they have to form, the atoms have to form molecules to complete outermost energy level with 8 electrons. We call complete octet. Outermost energy level is valence shell. The valence shell, when the valence shell has 8 electrons, means complete in octet. Such one we call stable atom. Except 18 groups element, all elements have less number of electrons in outermost energy level. Therefore, they have to form bonds with other elements. But when you take all 18 elements, 18 group elements, xenon form compounds with the highest electronegative elements like oxygen and fluorine. Oxygen and fluorine. So they accept 18 groups element. Other elements need to form bonds to complete their valence shell with completing 8 electrons. That's why we need to consider their valence electrons. When you take nitrogen, nitrogen belongs to 15 group. 15 group. So it has only 5 electrons in valence shell. To take the 8 electrons in the valence shell, it needs 3 more electrons. That's why it forms bonds with 3 hydrogen atoms. So NH, 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 these bonds we call bond pairs, and the single 2 electrons which are not formed bonds and freely available on nitrogen, valence shell. That's one we call lone pair. So even atom in the in the valence shell of the atom has only electrons, right? Means freely available electrons. Molecule has bonded electrons as well as freely available electrons. Therefore, valence shell electron pair repulsion. Electrons pair repulsion. In between electrons, they have repulsion because electrons are negatively charged particles. Electrons are negatively charged particles, therefore they repel each other. So when you take ammonia molecule, it has two kinds of electrons, lone pair, 2 electrons, and bonded pairs. Bonded pairs, bond is formed by sharing electron, 1 electron of nitrogen and 1 electron of hydrogen. So there are moments, right? Freely, right? The electrons in the bonds cannot freely move. Compare with lone pairs. Compare with lone pairs. Therefore, repulsion highest on lone pairs than bond pairs. Repulsion is greater. Freely available, right? Freely move. The lone pairs, the free electrons can freely move. So they can repel each other easily. But here, bonded, right? Their moments is restricted because of the bonds. They have sigma bonds. So sigma bonds formed by overlapping electrons linearly. So linear overlap is strong than freely available electrons. Therefore, repulsion in between lone pairs is greater than bond pairs. When you take water molecule, so this is the water molecule, the structure of water molecule. There's 2 lone pairs on oxygen atom. Oxygen belongs to 16 group, so it should have 6 electrons in valence shell. So you can count 1, 2, 3, 4, 5, 6. 6 electrons around the oxygen atom. It needs 2 more electrons to complete the valency. That's why oxygen combined with 2 hydrogen atoms to complete octet of oxygen. So when you take oxygen atom, it has 2 lone pairs and 2 bonded electrons, bond pairs. 2 lone pairs, 1 and 2. Here another 2 bond pairs. So then when you take repulsion, the repulsion may occurs in between lone pairs, right? In between lone pairs, and lone pairs, bond pairs, and bond pairs, bond pairs. So when you take the repulsion, the highest repulsion can be seen in between lone pairs. So lone pairs, repulsion is highest. Greater repulsion in between lone pairs. Then lone pairs and bond pairs. Lowest repulsion in between bond pairs and bond pairs. Right? Bond pairs and bond pairs. The repulsion is restricted by some amount for the bonds in between bonds. That's why the repulsion is lowest in between bond pairs and bond pairs. So when you take water molecule, due to repulsion in between lone pairs, bond pairs, and bond pairs, finally the structure will change to angular. That's why bond angle of water molecules says 104.5. Right? So VSEPR pairs means lone pairs or bond pairs. VSEPR pairs count for the electrons in the valence shell. When you take the atom, valence shell has freely available electrons. But when you take the molecule, it has bond pairs as well as lone pairs. Right? So restriction, the moments of the repulsion is little restricted for the bond pairs than lone pairs. So repulsion is greater for lone pairs. So all VSEPR units, right, can be categorized into two groups. Valence shell, electron pair, repulsion units can be categorized into two groups as bond pairs and lone pairs. Bond pairs and lone pairs. Bond pairs may be single bonds. Single bond or double bond or triple bond. For example, for the molecule having only single bonds, we can take CH4. In between carbon and hydrogen, they have only single bonds. When you take the molecule like carbon dioxide, it has double bonds in between carbon and oxygen. When you take the molecule, simple molecules having triple bond, as example, we can take carbon monoxide. Carbon monoxide here plus charge, here negative charge on carbon atom. So single bond, double bond, triple bond is one of the VSEPR unit. And lone pairs, right? Lone pairs. For example, when you take chlorine atom, chloride, right? Atom, it has three. Sorry, four lone pairs, or instead of that, you can take ammonia. So nitrogen atom has one lone pair. Here, two pair of freely available electrons we call lone pair. So when you take VSEPR units, one of single bond, one of double bond, one of triple bond considered as one VSEPR. Clear? When you take one of single bond, one of double bond, one of triple bond, we consider as only one VSEPR unit. Only one VSEPR unit. When you take lone pair, one of the lone pair. One of the lone pair also considered as only one VSEPR. So by taking the VSEPR units around the central atom of the simple molecule, you can take the geometry of the molecule, shape of the molecule, hybridization, something like that, right? So the more simple information can be obtained from the Lewis structure of the molecule by taking the VSEPR units too. So you can note down VSEPR units may be bonded pairs and lone pairs. Bonded pairs, single bond, double bond, and triple bond. Single bond, one of the single bond, one of the single bond, one of the double bond, one of the triple bond considered as one VSEPR unit. And when you take one of the lone pair, it also considered as one VSEPR unit. For example, I take CH4 molecule. Here's the CH4 molecule. So it has 1, 2, 3, 4. Bond length should be same, right? Bond length should be same. So when you take 4 CH bond, all form single bonds. So they have 4 VSEPR units. Total VSEPRs are 4. 1, 2, 3, 4. When you take ammonia, so ammonia has 3 NH bonds, 3 NH bonds. Therefore, here one of NH bond, single bond considered as VSEPR unit, one VSEPR. So here one VSEPR, second VSEPR, third VSEPR, 3 bonded VSEPR units plus 1 lone pair. So totally we call 4 VSEPRs. 4 VSEPRs. 4 VSEPRs. If I take another example, I erase those 3. Right, you can note down. If I take sulfur trioxide, SO3, sulfur trioxide, right? This is the structure for skeleton, the structure for sulfur trioxide. So it has 3 double bonds. 3 double bonds. 1, 2, 3. 3 double bonds in between sulfur and oxygen atom. So one of the double bond considered as 1 VSEPR. Therefore, total VSEPRs around the sulfur atom is 3. 1, 2, 3. The total VSEPRs are 3. When you take carbon monoxide, here plus charge on oxygen atom, minus charge on carbon atom, even highest electronegative element is oxygen. So total VSEPRs around the carbon. So I'll take the total VSEPRs around the central atom, guys. Okay, central atom. So here central atom is carbon, because when we select the central atom and surrounding atoms, right? The theoretical we take the lowest electronegative element as a central atom. Central atom. So when you take the carbon, it has triple bond. So one of the triple bond considered as one of the VSEPR. So total VSEPRs around this carbon atom is 2. When you take ICl2 minus, here ICl2 minus, iodine has low electronegativity than chlorine atom. That's why iodine is a central atom. So completing octet, each chlorine has 3 lone pairs. Central iodine has 1, 2, 3, 4, 5, 6, 7, 8. Negative charge on iodine. So first one I took here is sulfur trioxide. Here carbon monoxide. Here ICl2 minus. So when you take total VSEPRs around the central atom, it has 2 single bonds. So one of the single bonds considered as one of the VSEPR. So there are 3 lone pairs. 3 lone pairs. Therefore, it has 3 lone pairs as VSEPR units. So total VSEPR units around the iodine is 5. The next one we can take. I'll take carbon dioxide. Here carbon dioxide. This is a Lewis structure for carbon dioxide. So there are 2 lone pairs. 2 double bonds in between carbon and oxygen. Right side has one of the double bond in between carbon and oxygen. The left side also have one of the carbon double bond in between carbon and oxygen. So total double bonds, right, around the carbon is 2. So one of the carbon double bond considered as one of the VSEPR. Therefore, total VSEPRs around carbon is 2. If I take one more example, I take SF3N. 1, 2, 3, right? SF3N. SF3N. Central atom is sulfur. There are 3 fluorine atoms around sulfur and triple bond nitrogen atom. So each fluorine has 3 lone pairs. Okay. Right. So one of the triple bond considered as one of the VSEPRs. One of the single bond considered as one of the VSEPRs. So total VSEPRs around the central atom is 1, 2, 3, 4. Total VSEPRs are 4. When I take another one like oxalate ion, C2O4 2 minus. Here's the oxalate ion, Lewis structure for oxalate ion. Right. When you take one carbon atom, around one carbon atom, two single bonds in between carbon and oxygen. The next single bond in between carbon. And there's a double bond in between carbon and oxygen. So total whispers around this carbon atom is 3. Around one carbon atom, it has 3 whispers, 3 whisper units. So we can take one more example. I'll take NO3 minus. NO3 minus, nitrate ion. Nitrate ion. Even nitrogen has positive charge. Don't worry about that because whisper units are any of double bond, any of triple bond, any of single bonds, or any of lone pair. So here 1, 2, 3 total whispers around this is 3. This is so how simple now, right? When you know the total whispers, you can tell the hybridization too. In advanced level syllabus, we have to know 3 types of hybridization. 3 types of hybridization. The first one is P, the second one is P2, the third one is sp3. Sp, sp2, and sp3. Sp means one of the electron related with s orbital and one of the electron related with the p orbital. So overlapping electron belongs to s and p. They form sp hybridized orbital. sp2, one of the electron belongs to s orbital and 2 of electrons belongs to p orbitals. So one of the electron and 2 of electrons of p overlap to form sp2 hybridized orbital. sp3 means one of the electron belongs to s orbital and 3 of p orbitals, right, overlap each other to form sp3 hybridized orbitals. So sp means 2 whispers, one for s, another one for p. So when we have 2 whispers, we call the hybridization as sp hybridization. For sp2, 1 for s, 2 for p, so totally we have 3. Therefore, when we have 3 whispers, we call sp2 hybridization. When we have 4 whispers, 1 for s, 3 for p, the totally we have 4 whispers, we call sp3 hybridization. Right? 4 whispers, sp3 hybridization. Now you can tell the hybridization of the salt atom here. 3 whispers, so it has sp2 hybridization. With the hybridization, we can tell the geometry and shape of the molecule. And with the hybridization, we can list or arrange according to increasing order of the electronegativity of the ions or molecules which are the same central atom. We will discuss that part with the next video. So when we have 2 whispers, one for s, another one for p, therefore sp. When we have 5 whispers, it's not included in your syllabus, but I'll explain how to get. We have 5 whispers. 1 for s, because to form the bond, we should have 1 unpaired electron. S orbital, right? I'll explain here. The maximum orbital for the S is 1. P4, right? 3. There are 5 orbitals for the D. Do you know that? Asymmetrical quantum number, magnetic quantum number, right? You know that. To take the one of the electron, one of the atoms should give the one of the unpaired electron, and the other element should give the unpaired electrons. So when you take ammonia, nitrogen should give one free electron, one unpaired electron, and hydrogen should give the one unpaired electrons. So unpaired electrons pairs to form the bond. Therefore, maximum number of electrons can contribute by S orbital is 1. So maximum unpaired in S orbital is 1. When you take P, maximum unpaired electrons can be taken by P orbital is 3. Here 1, here 2, here 3. That's why we stop at sp3. Right? sp, 1s, 1p. sp2, 1s, 2p's. sp3, 1s, 3p. So we can't take sp4. What happens when you take p4? You have only 2 unpaired electrons. We can't make the bond by taking the electrons already pair in the orbital. We can shift into d orbitals. Hybridization theory, right? So this little bit difficult to get the theory, right? But when you take the answer simply by taking the orbitals, right? Don't think about this. When we take in the hybridization, like PO43 minus, PO43 minus, it forms 5 bonds by shifting one of the electron to the d orbitals. Right? You should know that. I'll explain that part with the next video. Right. So you should have 3 unpaired electrons to get the sp3. So the next electron, if we have more VSEPRs, we have to move to the d orbitals. Right? D orbital. So sp3, then sp3d. sp3d means D has unpaired electron. sp3d, 4 VSEPRs. sp3d, 4 VSEPRs. sp3d2, 5 VSEPRs. Right? 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6. When you have 6 VSEPRs, it should have sp3d2. sp3d2. Right? Then when we have more than that, sp3d3, sp3d4, sp3d5. Right? Okay. So when we have 5 VSEPRs, 1 goes to S, 3 goes to P, the remaining 1 goes to D. Therefore, hybridization is sp3d. sp3d. Now you know for the 2 VSEPRs, the hybridization is sp. Here, central atom has only 4 VSEPRs, therefore sp3. sp3. Around 1 carbon atom, 3 VSEPRs, therefore sp2. Around nitrogen atom, 3 VSEPRs, therefore sp2. So, if you know how to draw the correct stable Lewis structure, from the correct stable Lewis structure, you can take the total VSEPRs around the central atom. From that, you can take the hybridization. From that, you can get the shape, geometry, and you can rearrange according to increasing node of electronegativity for the molecules or the ion which form by the same central atom. Right? If I take one more examples, right? I take sulfate as the next few examples. I do more few examples. If I take sulfate ion, it's so 4, 2 minus. sulfur, 2 double bonds in between oxygen, and 2 single bonds in between oxygen. So total whispers, now you know how to get the total whispers around the central atom. Here 1, 2, 3, 4. 4. Therefore, hybridization is sp3. Hybridization is sp3. When you take sulfide ion, SO32 minus sulfur, oxygen, single bonds, and to complete the valency of the sulfur, 1, 2, 3, 4, it should have 6 electrons. We have get 1 lone pair. So total whispers around the sulfur atom, 1, 2, 3, 4. Again, sp3 hybridization. sp3 hybridization. Okay, guys. When you want to take the hybridization for the carbonate, so carbonate ion is this one. Around the carbon atom, 3 whispers, sp2 hybridization. When you take SF6, around sulfur atom, there are 6 fluorine atoms. This is the Lewis structure. So total whispers around the sulfur is 6. So how to write the hybridization? 1 for S, 3 for P. The remaining 2 goes to D, sp3 D2. sp3 D2. Right. Okay, guys. So I think you have get clear understand how to get the whispers after drawing correct or a stable Lewis structure for the given molecule or ion. When you know the total whispers around the central atom, easily you can get the hybridization of the central atom. Right? This is a really simple theory, but most of students get wrong answers for the questions when we have given to the papers. Right? Putalagi papers valada anivariyama make equations enavamai, right? Especially for the first term test paper, right? Most of questions related with the second unit, and this one is the second unit chemical bonds part, right? Part of the chemical bond lesson. So please take the weekly understand, practice with the different structures, different molecules. So if you have any doubts related with the whispers, you can ask any questions. And this is my WhatsApp number. You can ask any question, giving simple message to 0710-171-475. Right. So thank you very much. And we'll continue with the next video. Thank you.